A big thank you to Dr. Francesco Topputo for doing the third episode of the Space Engineering Podcast with me. In this one, we talk about the Asteroid/Lunar CubeSat mission design and trajectory optimization, and we break it down into three missions that he's been working on. The first one being the Milan CubeSat, which is part of a joint mission between NASA and ESA for a mission to a binary asteroid system called Dimorphos. And the second one is the M-ARGO CubeSat, which is the first standalone CubeSat to ever go to an asteroid starting from L2 Sun-Earth halo orbit. So we talk about the trajectory optimization that he did for that. And the third one is LUMIO, which is another CubeSat that he's working on that's going to go to the Earth-Moon L2 halo orbit. So, starting off with the Milani CubeSat, we go over the details of how it's a joint mission between NASA and ESA, going to the binary asteroid Dimorphos. And Milani is a CubeSat that will be deployed from the main spacecraft called Hera. It's one of two CubeSats. The other CubeSat is called Juventus, and I actually got to do some work for that one as well when I worked with GOMSpace. And then we get into the details of the trajectory trades. So they had three different options that they had for trajectories when they were doing this preliminary analysis. The first one was three-body proximity solutions, so something like a halo orbit. The second one was closed orbits, so something like an equatorial orbit or a terminator orbit that is a closed orbit. And the third one was hyperbolic arcs, which if you're watching this on YouTube, I have a visual right here on the right that shows the trajectory of Hera and how it's doing the hyperbolic arcs around Didymos. So what we're referring to with hyperbolic arcs is something like this. So they're doing something similar to that. We also talk about the inter-satellite links between Hera and the two CubeSats, collision avoidance, and then also they do plan on doing a landing on the little moon called Dimorphos, which is pretty exciting. And then I've also made a video using NASA Cosmographia illustrating this Didymos system and trajectories to give a better feel of what we're talking about when we're talking about this Milani CubeSat and the trajectories and the trajectory trades that we're doing. So be sure to check that out on YouTube. I'll have a link in the description if you want to kind of get a visual feel of what's going on. So the second mission, M-ARGO, we talk a lot about the trajectory optimization that went into that. So it's a low thrust trajectory optimization program, how he went about doing that, how to set up mathematically the two-point boundary value problem and how to solve it using calculus of variation, and then the two trades that they did for time and fuel efficient trajectories, how to get those solutions, and then again setting up the problem with Lagrange/a co-states vector and the equations of motion that they used. And then for the LUMIO CubeSat, which is the last one, we went over again the trajectory trades, why they chose an L2 halo orbit for that mission, what were the lunar observation requirements that were also satisfied with the L2 halo orbit. We talk about how they're going to be dropped off, or the trade study assumes they're going to be dropped off in low lunar orbit. So how to do that transfer between low lunar orbit and L2. How to do the orbit determination for that orbit in that system. And then we get a little bit into the details, not too far, but definitely a little bit into stable and unstable manifolds that go into getting into Lagrange points and halo orbits. So yeah, that's pretty much it for the introduction. And without further ado, here is the third episode of the Space Engineering Podcast with Dr. Francesco Topputo. Okay. So, since we're only going to have 30 minutes on this round, I think we might as well just get straight into the technical stuff, which I'm excited about. So first, can you give an overall, just general overview of the mission and the objectives of the Milani CubeSat?
Sure. Milani is one of the two CubeSats that will be released in the proximity of a binary asteroid called Didymos, and it's part of the European-led mission called Hera. Hera is or Hera, depending on how you want to pronounce it. Hera is a European Space Agency mission that will visit a binary asteroid where we have the main asteroid called Didymos and its little moon called Dimorphos, that will be in turn visited by the NASA mission DART, which is a mission led by the John Hopkins. All right, so in essence, the entire program, it's a NASA-ESA cooperation, is called AIDA, Asteroid Impact and Deflection Assessment. So it works this way. There is the DART probe that is going to impact the little moon, Dimorphos, in 2024. And then Hera will follow up 3 years later, so in 2027, at the beginning of 2027, it will reach the asteroid and study the binary asteroid system and, moreover, the crater produced by the impacts of DART with Dimorphos. So in this framework, the European Space Agency included 2 CubeSats to be released in situ, because I mean you can do some bonus science with CubeSats in deep space. They are cheap. They can be developed in quite a short amount of time, and moreover they are light. So while the Hera spacecraft has to be operated in a very conservative and cautious way, CubeSats can do fancy things around the asteroids. So there will be Juventus with the radar orbiting at low altitude around the bigger asteroid, the Didymos, while there will be Milani, and this answers your question, that will hover in front of the asteroids, because it has a passive payload. It will do some sort of back and forth motion in front of the asteroid. When I say in front of the asteroid, it means in the day side of the asteroid, and trying to study the 2 bodies in a gradually approaching way. So we will have a far range operation phase in which we are 10 kilometers far from the body, and we will gradually move closer and closer and closer to the bodies, all the way until attempting a landing on the smallest asteroid. So we are aiming to land on the smaller asteroid, and in particular, before that, we would like to take close-up images of the crater, because this will serve the purpose of having a better understanding of the kinematic impact between DART and Dimorphos.
Mm-hmm. Okay, so I'm super interested in learning more about the trades that you had as far as the trajectories that you're going to have around the asteroid. So in the paper that you sent me, there was basically 3 options you looked at: the hyperbolic arcs, the closed orbits, and the 3-body proximity solutions. So I want to get into all 3. But first, I'd like to talk about the 3-body proximity solution. So basically, is that staying in a way a halo orbit? Because is the gravity of those bodies large enough in order to do something like a halo orbit, especially with the solar radiation pressure perturbation?
Sure, in principle, yes, but there is a but. Mm-hmm. So the system is made of this bigger asteroid, Dimorphos, let's call it D1, and the little moon, Didymos D1, and the little moon Dimorphos, let's call it D2. So D2 revolves around D1 in a quasi-circular motion. Therefore, when you have a massless particle, a CubeSat, wandering in this system, you can formally state the problem as a circular restricted 3-body problem. And so far, so good. The CRTVP has 5 equilibrium points, and 3 of them are collinear, 2 of them are triangular. And the orbits you were mentioning, the yellow orbit, occur around each of the 3 collinear points. They have been very useful to design missions for what concerns observation of the sun, or deep space telescopes at Sun Earth 2. Not even to mention those at the moon, where we have another mission study called LUMIO that is revolving in one of these kind of orbits. Now, the issue with the system, and the reason why these kind of orbits were discarded, is that the Lagrange point in this system is located at few meters above the surface of the body. Now, when you're flying a spacecraft, you never know exactly where the spacecraft is, especially if you are in the deep space. Usually you carry out a number of measurements, for instance, radiometric based, in order to solve for on ground for the position of the spacecraft. But even though you have a lot of measurements, usually you are not sure of the deterministic location of the spacecraft. Usually you have a nominal state plus a covariance, which is the locus of all possible points in space where the spacecraft can be. Now it turned out that if you consider all of this ball around the nominal point of uncertainties, it's like a cloud of points where the spacecraft can be. Well, it turned out that it was not safe at all to go to one of the Lagrange point orbits because they were so close to the surface of D1 that impacts could not be ruled out of the analysis. And this was the main reason for discarding them.
Okay, that's interesting. So how do you go about categorizing or figuring out what your kind of error ellipse of your position is going to be? Because I think you talked about in the paper there was optical navigation as part of your orbit determination system. So yeah, so how did you go about quantifying that in that trade?
All right. So in this particular case, we have a fusion of measurements in order to gain confidence with the knowledge of position and velocity of the spacecraft. Milani, Juventus, and Hera, they have a system, and for the first time, they will try to perform a intersatellite link in an asteroid environment. Okay. Now, there are 3 radios on board. The main one is on Hera, and the other 2 are on the TU CubeSat. And the TU CubeSat can exchange with the mothership their information, and as a byproduct of this, for instance, the telemetry and the scientific data have to be relayed on ground by passing through Hera. As a byproduct of this, Hera can measure the distance, so the range between the mothership and each of the 2 CubeSats, and the range rate by Doppler effect. Now, these are the information that you can use to solve for the position. On top of this, as you said, you can include information coming from images that you can take to the bodies, and you can increase the knowledge by putting in the equation also the line of sight, for instance, to certain markers or to certain surface features typical on the 2 bodies. On top of this, we have also a LiDAR, which is a laser altimeter, that can be also used in order to, for instance, to solve for the range to the main body between the CubeSat and D1 itself. So if we put all of this in the equation, the method that you have to use is the state estimation method, which is typical of the orbit determination step. In our case, we use extended Kalman filters, purposely modified for the application at hand, and we have some quite good results, meaning that we'll have uncertainty that can range up to 100 meters, in just to give you an order of magnitude of the uncertainties that we will have while in the asteroid environment.
Okay, that's pretty cool. So and I want to get into the second option that you had in your trade for proximity operations, which was closed orbits. So is that referring to something like a terminator orbit?
Also terminator orbit. Closed orbits were like orbits that revolve all around the main asteroid, so D1. And they can be either equatorial or, as you said, terminator orbit, which is an orbit that lies on the terminator plane. Now, why they were discarded? First of all, the equatorial orbits, no way. So we do not want to go in the night side of the asteroid, simply because if you take a picture of the asteroid when you are in the night side, you have no information. And because of the knowledge analysis that I mentioned earlier, you will increase the uncertainty on the state a lot. So it's a risk that we do not want to take. So we don't want to go on the night side of the asteroid. The other strategy would be to put the orbit in a so-called SSTO, Sun-Synchronous Terminator orbit. However, this did not match with the scientific requirements that we have, because we have a payload that is a spectrometer, and the guys behind the instrument, they want to imagine the asteroid at low phase angle. What does it mean, low phase angle? Imagine you are the CubeSat and your eyes look at the asteroid. You want to have the sun behind you, ideally aligned. You want to have the sun, the CubeSat, and the asteroid all on the same line. This would mean 0 degree phase angle. Okay. Now, the guys in charge of this instrument have issued requirements that we have to take measurements at low phase angle. If you go on Terminator orbit, you have 90 degrees phase angle, which is not compliant with the requirements. And that's why those orbits were discarded as well.
Okay. Okay, yeah, so at that point, when you have the instrument requirements. So were there any other instrument requirements, either from any of the instruments that are going to be on board, that also limited these trades?
Yes, still the same instrument. There is another instrument called Vista, which is measuring the impacts of the micro dust particles. It's a high sensitive system, I would say. Don't ask me how it is made of, because I have no idea, but it is very sensitive, and this measuring the little dust particles that will impact, hopefully, with the CubeSat. And this is to solve for the problem of understanding if there is a cloud of dust even all around the asteroids, because on comets it's straightforward, but on asteroid you can have little particles that orbit the asteroid, for instance, which you cannot detect unless you have this very precise instrument. And this is designed and developed in Italy. While the other spectrometer, the one that I was referring earlier, has other requirements in terms of observation of the crater. So point is that the system has the D2, so the little asteroid, has a circular orbit around D1, or is thought to revolve in circular orbit around D1. Moreover, there is the assumption that the moon is in a one-to-one spin orbit resonance, like our moon is in resonance with its orbital motion, and we always see the same side of the moon, okay, the near side. Now the same appears, the same is assumed for the little moon around the big asteroid, which means that if you have a crater that you want to look at, this crater is revolving, is rotating, okay, on around the moon spin axis in the same fashion as the orbital motion. And this is quite hard, because it's imposing very specific geometry, observation geometry, and we are studying this problem, and we have identified a geometry that blocks the problem, and some points that we are calling key points, where you have to fly through these points. And when you're flying in this key point region, you have to take this kind of measurement. So the answer to your question is that there are no other instruments that are affecting the trade-off, but however, it's the same instrument, but other kind of measurements that are actually strongly affecting the trade-off.
So does the DART mission know at what point on the surface of Dimorphos, the moon, they're going to impact? Because that will also affect
Yes, we are. Yes, we are assuming, of course, there is a tight cooperation between the two agencies, and the baseline is to aim to the leading side of the moon. So the side that is aligned with the velocity vector of the moon. Okay, so the assumption that we are making is that the crater will be at on the hemisphere that belongs to the leading side of the moon.
Okay. So then, now that we've gone through the closed orbits, can we then get to the hyperbolic arcs that you guys decided on this trade? That's going to be what you're going to be moving forward with?
Yes. So these arcs are called safely hyperbolic arcs, because the issue is that if you by chance or by mistake you miss a maneuver, it's inherently safe. It means that in the worst case, you will get away, you will move away from the system, but eventually you will not impact with either of the two asteroids. So it's inherently safe in this sense, because they are open orbits, okay? And we perform some sort of back and forth motion on jumping from one hyperbola to another, and to another. That's why we went for this kind of inherently safe orbit for the Milani design. Of course, there are no free meals, so this inherently safe solution comes at a cost. The price to pay for this is that at every maneuver point you have to reverse the velocity vector. But fortunately, we are talking about extremely weak gravitational environment, so extremely weak vector fields. So at the end of the day, this can be done with almost no problem. We are accomplishing an entire mission with a delta V budget of, I mean, just to give you numbers, because I cannot give you the exact numbers, since the design is fluid and this is changing. So a number between 5 and 10 meter per second is the total delta V budget for Milani, which is ridiculously low if you think of typical space mission, deep space missions. So you have to maneuver frequently, but you are in low gravity environment, so maneuvers are quite easy to accomplish and cheap.
So I'm wondering, again, a little bit going back into the certainty of orbit determination, where you have these delta V's maneuvers on these hyperbolic arcs that are so small. If I remember correctly, maybe somewhere in the range of centimeters per second.
Exactly.
So I'm wondering if, first of all, what hardware, I know this isn't your side of the field, but on the hardware requirement side, what is the mechanism that's doing that delta V, like a cold gas thruster? And how do you measure, okay, we moved centimeters per second?
Sure. So the first part of the question, yes, we use a propulsion system that assures 6 degrees of freedom control. So it's made of a number of different little nozzles in the corners of the CubeSat that can exert either a force or a torque or both of them. So in principle, you don't even have to repoint the CubeSat along the desired position, but you can, even by locking the asteroids in the field of view, you can have translational motion by a suitably defined combination of the little thrusters that you have in the corners. Second part of your question is how you're going to measure this. Well, we are thinking of using an accelerometer on board.
Okay.
And the idea is to take samples across the maneuver, to download this information on ground, and as part of the orbit determination that is done on ground, together with radiometric data, pictures, LiDAR that I mentioned earlier, one has to also consider the data coming from the accelerometer.
Okay. And one of the things on these hyperbolic arcs that you mentioned that is it's safer than the other ones because if you miss maneuvers, it's okay. And I'm wondering, in the paper, there was also some talk about entering chaotic three-body dynamics. So does that go back into kind of how you can model the system as a circular with restricted three-body problem plus solar radiation pressure? So yeah, what kind of chaotic three-body motion was being referred to there?
That part refers to the typical orbits that you can have in the CRTBP that are not Lagrange point orbits. For instance, you can have another kind of orbits that are quite famous in the literature are these DROs, so distant retrograde orbits, or other kind of similar orbits, which means that you have periodic orbits that take into account two simultaneous gravitational attractions on the CubeSat itself. So the one from the main asteroid and the one from the little moon. Again, these orbits were deemed too much unstable, and they were not considered, and they were discarded because the inherently safe hyperbolic arcs were deemed most suitable. I want to mention about the SRP, the solar radiation pressure that you mentioned. I said that this is an extremely weak gravitational environment. It is so weak that the SRP is the leading, above certain altitude, the solar radiation pressure is the leading force, is the leading acceleration. So if you do not maneuver, it will swipe out the CubeSat from the environment. It's some sort of self-cleaning environment. If you don't maneuver, you will be pushed away from the solar radiation pressure that you have there. So I mean, I wanted to follow up what you said, saying that it's a perturbation. It's usually thought as a perturbation, is something that you can cancel out. But in this environment, it's not only a perturbation, is the main component of the right-hand side.
So I'm wondering, you mentioned that there's a 0 phase angle requirement that was met by doing the hyperbolic arcs. And I'm wondering kind of what other requirements from the instruments, what other requirements were coming from the instruments that also kind of made hyperbolic arc, this is the best decision for us.
Yeah, sure. So there were basically two requirements. One was the one on the phase angles that you mentioned. The other one was a requirement on the ground sampling distance, so the spatial resolution with which you can acquire images of the asteroid. So while the phase angle is used to set the angular position of the CubeSat with respect to the system, the one on the resolution is imposed, it's translated as a distance, because with the given field of view and focal length, you have a certain spatial resolution, which is a function of the distance. So at the end of the day, if you have a phase angle bound, it means you have a cone that emits from the asteroid, while if you have a ground sampling constraint, you have a sphere. So by the intersection of a cone and the sphere centered at the asteroid, you have a certain region. You have a certain region where you may want to stay. And again, this region does not cope with any of the Kepler motion or Kepler-like motion that you can have around the asteroid. So you cannot revolve around the asteroid because it's a region. It's like a tile which is between the sun and the asteroid. Okay. Mm-hmm. on the day side of the asteroid. So you have to be in this some sort of tile, which is not a flat tile, but it's banded and it's lies on a piece of surface, on a piece of sphere, and then you have to be there. So the only reason for being there is to go for some sort of hovering above the asteroid. That's in essence the rationale behind the choice that we made.
And then were there also any relative velocity or relative like spacecraft attitude slew angle as you're imaging the moon or the main body that were also satisfied by the hyperbolic arcs?
Sure. As I said, the environment is very low gravity, so the relative velocities are very, very low. We are moving relative to the body in the order of a few centimeters per second, which means that you're right, you have to keep pointing the asteroid, but before you are moving so slow, pointing is really feasible because it's really slow, and it's compliant with the onboard systems that you have in terms of the DCS system. But so, yes, you have to keep pointing the asteroid, of course.
So I'm wondering, because you mentioned earlier the inter-satellite link between the Milani, the Hera, and the Juventus. So I'm wondering what kind of information is being relayed between the spacecraft, and is it also Milani and Juventus talking to each other, or is it just the two CubeSats talking to Hera individually?
All right. So through the inter-satellite link, the three spacecraft has to exchange telemetry commands, telecommands from Hera to the CubeSat, and scientific data, like the images that we take cannot be relayed on ground, but they have to go through Hera and then from Hera to ground. So that's the amount of type of information that they can exchange. For what concerns the link between Juventus and Milani, yes, there is in principle the possibility of performing a fully triangulation. So Milani can talk to Hera and Juventus, and the same for Juventus. So far, in this phase of the project, we haven't exploited it yet. So far, we are always talking about Hera, talking to Juventus, and talking to Milani, but the two CubeSats talking to each other, it is feasible. That's a matter of radio science experiment that they are going to fly, which I'm not fully confident with.
Okay. And then I'm also wondering, as far as the links and the trajectories, the kind of the risk collision and collision avoidance that went into this study, especially with if Juventus is also going to be in the proximity of the system. I'm kind of wondering how you go about maybe quantifying or mitigating risk collision, I guess not just with Juventus, but then with Dimorphos as well.
Yes, exactly. It will be a crowded place at some point, and we may want to be sure that the spacecrafts do not collide each other, and or they do not collide with each of the two asteroids. So you're right. So we have been discussing this. Pretty recently, and the idea is that the ground control has to run this kind of checks by doing the so-called knowledge and dispersion analysis, which gives you the envelope of all the possible positions where the spacecraft can be, by using the statistical approach that we mentioned earlier. And if the risk is above a given threshold, the plan is to perform a CAM, collision avoidance maneuver, So we're budgeting a tiny amount of propellant fraction to be allocated for this kind of maneuvers, which are being considered in this phase of the design.
Okay. And then I think getting to the end here of talking about Milani, I'm really curious that you mentioned that there's going to be an attempted landing on Dimorphos. So I'm wondering kind of that analysis of how you go from the hyperbolic arcs to, say, a rendezvous trajectory with Dimorphos.
Sure. So the entire mission concept works in a slight and progressive approaching from far away all the way to near to the Didymos system. Now, at the end of the two science phases, which are called far range operation phase and close range operation phase, in which we are in this tile like region, despite not being compliant with the mission requirements, we will carry out a phase which is called experimental phase, in which we go on a sun-synchronous terminator orbit. So this is an orbit 90 degree on the equatorial plane. And from this orbit, we once again decrease the altitude of the CubeSat all the way down to 2 to 3 kilometers on D1. So if you consider that the moon, we go down to 2 to 3 kilometers on D1. And from that point, we do a targeting of D2. Well, now the challenge is that once you are on the terminator orbit, you cannot see D2 because D2 is on an equatorial orbit. The two planes are orthogonal to each other. So as it happens in the entire space trajectory design, you have to trust the point where you are going, and you have to rendezvous with D2 in a certain location of space. This poses a little bit of challenges in terms of relative navigation before landing, which we are still assessing. But this is the strategy that we are following to design the landing trajectory.
Okay, and I know that you said you're in the pretty early phases of this design, but I'm wondering if you've gotten there yet, the types of relative velocities that you'll have when you do the landing, where it's like a meter per second, or if you're getting really precise.
No, it's much lower than a meter per second. Now, if I remember correctly, but please don't quote me on that, the escape velocity from D2, so from Dimorphos is lower than 20 or 30 centimeters per second.
Oh, okay.
Which means that if you land at 1 meter per second, you're probably bouncing on the surface of the asteroid, and you are escaping the system. So we are making sure that the touchdown velocity is a little bit lower than the escape velocity itself, such that if you dissipate a little bit of the kinetic energy, the rebound trajectory does not kick you out of D2 system.
Okay, so I think I've had pretty much all my questions for Milani. And if we could, I'd like to move on to M-ARGO now, which I guess for context is where we first met when I did an internship in Luxembourg at GOMSpace. So could you give kind of a brief overview of the mission objectives of M-ARGO and then the work that you led in that summer of 2019?
Sure. So M-ARGO, let me say that it's one of the most exciting mission concepts around, because it's the very first standalone deep space CubeSat. You know that there are two main concepts behind interplanetary CubeSat. So the first one is to release them in situ by using a mothership, like Hera will do. It will bring the CubeSats with it and release them when it will be in the asteroid environment. Or the other concept is the concept of standalone interplanetary CubeSat. Now, this is much more challenging because it means that you launch the CubeSat in some sort of either Earth escape orbit, or you park them in the Sun-Earth L2, like in the case of M-ARGO. And from that point on, the CubeSat by itself, by using its own miniaturized propulsion system, it has to accomplish the transfer all the way to the target. So M-ARGO belongs to this second category of CubeSat, and it's thought to be the first standalone interplanetary CubeSat to accomplish a deep space cruise to a target asteroid by using miniaturized ion propulsion. It's a fantastic technological demonstrator because it has a number of technologies in it, just to mention few: miniaturized ion propulsion, miniaturized X-band transponder, and reflect array for communication with the Earth. Deployable antenna, talking about. So it's a technological demonstrator, but to demonstrate these technologies, you have to do something. So since you are going to an asteroid, you can also do, as a byproduct, some science with it. So by chance, I'm not sure how much chance there is there, but the payload that M-ARGO will carry is exactly the same as the one in Milan. So it's the same spectrometer, manufactured by the same people, and so on and so forth. So once then you can do spectrometry, so you can characterize the composition of the asteroid in view of the future in situ resource utilizations. So you know that there are these concepts of asteroid mining and so on. So the idea is to characterize the composition of the asteroid for a future possible exploitation of these resident space objects. In terms of what we did at Polimi, at Politecnico di Milano, we were responsible of the mission analysis for the phase A of M-ARGO. And we had to do two main tasks. One was the so-called neo-target screening, in which we carried out a massive computation to assess which asteroids were reachable from by M-ARGO. And once we compiled a short list of 5 targets, and once we have the 5 targets, we had to carry out a detailed mission analysis for what concerns the deep space cruise. So characterize all the transfer trajectory in a high fidelity environment, and extracting a number of information that were later used by the partners at GOMSpace that were in charge of the system design.
So I want to get into the details of the work that you did from going from tens of thousands of near-Earth asteroids down to a few. So can you talk a bit about how first you want to? Well, first is getting a trajectory from, if I remember correctly, it's starting from Sun-Earth L2 orbit and then going to all the asteroids. So can you talk a little bit about how you set up that problem of calculating those trajectories from L2 to the asteroid?
Sure. Yeah, before I forget, we have just published a paper on this, which can be found on Advances in Space Research. Can't remember on the top of my head the title by heart, but should be like, it should be something like Envelope of Reachable Asteroids by M-ARGO or something like that. So all the story has been now consolidated in that paper. But I'm very proud of the work that we did, because as you said, so we took the Minor Planet Center database, and we extracted all the asteroid in terms of information and, most importantly, orbital elements of them. And here we're talking about 1 million objects. We are talking about 1 million objects. Last year, they were in the order of 800,000. We checked it again, the database again this year, and we are over 900,000 objects. So I assume at the date of this chat, we should be around 1 million or so. Luckily for us, many of them are in the main asteroid belt, which was not important for our purposes. So I'm talking about the belt between Mars and Jupiter, because we would like to be between 1.1 to 1.2 astronomical units with M-ARGO. So we filtered it by using educated guesses from previous studies, mainly perihelion and apohelion radius and inclination. After this pruning, we ended up with something like 500 objects. Now, for these 500 objects, we had actually a 2 years departure window from Sun Earth L2 and up to 3-year transfer time. So for each target, we solved 2 problems. The first one was a time optimal problem, okay, for the 2 years window. We determined, if you think of a 2-dimensional space in which on the x-axis you have the departure epoch from the 1st of January 2023 to the 31st of December 2024 on the x-axis. On the y-axis you have the transfer time. You have a line, okay? You have a curve on this plot. Now, if the minimum of this curve was higher than 3 years, which was the constraint that we had, the target was pruned out of the analysis. Whereas if the minimum was below the 3-year threshold, we retained it. And we retained it to next step. Next step, we carried out for these, let's say, selected set of asteroids, we carried out a fuel optimal transfer, okay? So this time you have the time of flight that changes. So you have the departure epoch and the time of flight that changes. When you use chemical propulsion, these plots are called pork chop because they are in 3D like the shape of a pork leg, I guess. And then when you cut down the contour lines, it's so this pork chop plot in our case was departure epoch, transfer time, and propellant mass used in terms of color code. If the minimum propellant mass used was higher than the other threshold that we had on the propellant, which in this case was around 2.6 kilograms, the target was thrown away. Otherwise, it was retained. So out of those retained, we ended up with a little bit more than 100 targets that were reachable in terms of both propellant mass and transfer time. But some pork chops, then the automated process was over, and together with the colleagues at GOMSpace, we went out with the manual inspection of the pork chops. So there were some that had just tiny feasible regions in them, for instance. They were pruned out. Some that were trending worse, which means that with a delay in the departure date, they were not going to be feasible anymore. So they were threw away, and so on and so forth. So at the end of the day, we ended up with 40 good candidates. 40 good candidates. However, we had to accomplish a detailed mission analysis for only 5 of them, of course, for the sake of time and effort. So then we made a choice, and we looked at the chemical composition, the type of the asteroid, the type of the asteroid, because the composition is not known, the type of the asteroid, the assumed spin, angular velocity, and a number of other parameters, and then we deliberately or liberally choose 5 targets, and we go on with them.
So I'd like to get into the optimal control part of calculating these trajectories. So I'm wondering, basically, from how you set this up from an optical control sense and the math sense. So how did you go about, so you have your initial state, which is at L2 halo, and then you have the orbital parameters of whatever asteroid that you're going to calculate a trajectory to. So can you talk about that process of starting with that and then whatever constraints that you have, and then plugging
Sure.
it into software in order to optimize a trajectory using low thrust?
Sure. So in terms of software, we used a in-house software. It's called LT2O, Low Thrust Trajectory Optimizer, that we have developed since a number of years now. Okay. In terms of math, the problem is quite interesting. So you have, excuse me. So you have the initial condition that is fully given. When I say initial condition, I mean 3 position, 3 velocities, well, the position vector, 3-dimensional, the velocity vector, 3-dimensional, and the initial mass. So you have 7 numbers that are given at the initial time, and you have 6 numbers that are given at final time, which are final velocity and final position that have to match the one of the asteroid. Final mass is not given because you don't know how much propellant you will take to get there. So this optimization problem can be solved by using calculus of variation. In calculus of variation, you have that your problem dynamics with your objective function can be mapped into the so-called 2-point boundary value problem, which is a problem which you have ordinary differential equations, and differently from a standard initial value problem, in which the initial condition is fully given at the initial time and you can march forward in order to characterize the solution. In a 2-point boundary value problem, you have that the conditions are mixed. Some of them are given at the initial time and some of them are given at final time. Moreover, the dimensionality of the problem increases because instead of the 7 equation of motion, 3 for the position, 3 for the velocity, and 1 for the mass, you have 14 dimensional problem, because attached to these 7 components of the state, you have 7 components of the so-called co-state or Lagrange multiplier. So vector of co-states of Lagrange multipliers. So at the end of the day, you have 14 differential equations with 7 conditions given at the initial time, 6 conditions given at final time, which sums up to 13. You need another condition, otherwise the problem is ill-posed. The other condition is given by the fact that the final mass being not specified allows you, this can be proved mathematically, allows you to specify the value of the associated costate. So the costate associated to the final mass, lambda m, this is called lambda m, has to be equal to 0. So this can be proven mathematically. So at the end of the day, you have 7 conditions given at the initial time, 7 conditions given at final time. You have to determine the 7 lambda zeros, so the 7 values of the initial co-state, such that when you march forward and you integrate the 14 differential equations, the solution has to satisfy the given 7 final conditions. So it's a problem of the classic problem of finding the lambda 0 in a classic 2-point boundary value problem.
Okay. And then I'm wondering, so once you solve all these, so if I remember correctly, I think when you did a presentation at ESA, you said that doing all these trajectories took somewhere around like a month and a half of calculation time. So I'm wondering how you set this problem up as far as software and the computer clusters that you use in order to be able to do all these. So I'm kind of wondering.
Yeah, the key here was parallelization. So the problem could be easily, I would say, parallelized, because you have that each search to a given target was independent from the search to the other target. Of course, they were totally independent. Mm-hmm. So the key was to parallelize the process and to use one processor for a given target. And we have in my group we use a workstation made of 80 cores, 80 cores, and then we could have a massive parallel thread to do this. But despite that, if you want to solve the problem with quite good level of fidelity and resolution, moreover, then you need quite some time because it's quite heavy, and you have also to do some other tricks in terms of numerical continuation and so on and so forth. Because once you solve a problem for a given departure epoch and transfer time, to move to next grid point, you don't start from scratch, but rather you exploit the knowledge that you have gathered by solving the previous problem, and you actually use that solution as initial guess for next point. This is called numerical continuation, and we massively exploited that in our search.
Okay. And then I'm wondering kind of the fidelity of the equations of motion or the perturbations. So in the initial run, when you had around a few hundred asteroids, did you use a full fidelity like solar system model where you have the gravitational perturbations?
No, because in the initial run, I mean, we used the simple two-body problem.
Okay. With
the spacecraft and the sun. Later, we assessed that. I mean, in this way, you could do a relatively fast target scanning. Mm-hmm. In the end, when we conducted the high fidelity emission analysis, we saw that the error was in the order of 5% in terms of propellant mass.
Okay, and then so the high fidelity, that includes, I would guess, all the barycenters of the planets and then solar radiation pressure and the low thrust, obviously.
And yeah, and that's it. Yeah. So and restricted n-body problem with all the planets, SRP, solar radiation pressure, and low thrust propulsion. For the case of M-ARGO, since it's a high power mission for a CubeSat, the area to mass ratio is quite high, and therefore the contribution of the SRP is relevant, cannot be ignored.
Okay, cool. So I think that's all my M-ARGO questions now. So then if we could move on to LUMIO.
Sure.
So then, yeah, you're working on a lot of missions here. It's pretty cool. So could you give, again, a general overview of the LUMIO CubeSat and the objectives?
Sure. So LUMIO is a lunar CubeSat that will be placed in the L2 point, but this time L2 point of the Earth-Moon system, which is the Lagrange equilibrium point that is beyond the Moon, as seen from the Earth. And while orbiting, this time is a halo orbit around Earth-Moon L2, while orbiting in this halo orbit, the CubeSat has to monitor the lunar far side in order to detect the flashes that arise whenever a meteoroid impacts the lunar surface. Now, we are used to bolide that we see in the sky. When we see a meteoroid entering the atmosphere or a meteor, if it survives, it's a meteorite itself. So I was not aware a while ago of the difference between meteor, and meteorite, but now I know. We are lucky because we have a protective blanket, which is our atmosphere, that dissipates a lot of the kinetic energy of the meteorite by converting it into heat. In the case of the moon, this doesn't happen. There is no protective blanket. So all of the kinetic energy is deployed all the way to the soil, to the lunar soil, which means that it's a huge kinetic energy. You can imagine that a meteoroid the size of a kilogram, so the size of a baseball ball, can deploy the energy of a good bomb, I would say, like military bombs, this kind of stuff. 10 to the minus 3 TNT kiloton, just for give you a number. Okay. Which means that, so part of the energy goes in the excavation of a crater, part of the energy goes in the production of a seismic wave, part of the kinetic energy is returned back in the form of kinetic energy given to the particles, okay? A tiny fraction of it, 1 part over 10,000, is transformed into heat. Mm-hmm. So the surface heats locally, and it heats so much that you have very high temperature in the order of 2,500 kelvins, which means that you have a flashlight in the visible that is emitted after the impact. So if you want to characterize these impacts, you can either go to the lunar surface, or you can take a number of pictures and compare the old ones against the newer, and so on and so forth. Or you can do remote sensing. And we actually do remote sensing. We look at the moon and we are trying to detect spikes in the luminous energy in the visible spectrum, which last a few tenths of milliseconds. So I would say up to 50, 60 milliseconds, okay? If you are able to detect these flashes, then it's highly likely that that flash has been, can be associated to an impact of a meteoroid with the lunar surface. I said highly likely because it can be a false positive. And so you have to have some validation mechanism, either on board or on ground, to get rid of the false positives.
Okay, so I'm wondering about the trades that went into choosing the L2 halo orbit. So I'm wondering if you talk a bit about that, and does it have anything to do with the lighting conditions, which I would assume that would be easier to see these flashes if you're looking at the shadow side of the moon?
Yes. So that's a good point. So first of all, this kind of survey is done from ground nowadays by using ground-based telescopes. There are two main programs. One in the United States that is conducted by the NASA Marshall Space Center. And the other one in Europe is funded by ESA, and it's a telescope in Greece called Neliota. Now, by doing this kind of survey from ground, you have a number of drawbacks. Most important one are the fact that you are on the Earth, which rotates. You can do this only a few hours per day, of course, during the nighttime. And moreover, you have to do that. You have to do that when you are looking at the night side of the moon from ground, which means that you have to do that when you have the new moon. You cannot do it when you have the full moon. Otherwise, the signal to noise ratio will be so high that you cannot resolve for the little flash. So actually the flash is much lower than the noise that you have with the full moon. Moreover, you have the earth shine, which is the reflection of the sunlight that hits the earth, that is reflected back to the lunar surface. So you have a number of these constraints. We had a mission goal, or actually a science goal, that was associated to the fact of conducting this observation on the lunar far side, because even though there are a number of constraints, the near side can be somehow characterized from ground. So we said, let's go to look at the far side of the moon. Mm-hmm. And moreover, when you do this as a space-based observation, you can get rid of a number of constraints associated with the fact that you conduct this observation from ground. So most importantly, you are not rotating with the Earth, and you don't have the Earth shine. So the trade there was, so the criteria were that you have to monitor the lunar far side, and you have to get rid of the lunar illumination. So you want to monitor the lunar far side when it's dark, okay? Now, despite the title of the song, there is no dark side of the moon, mm-hmm. because both sides are either dark or illuminating, depending on the phase of the moon. So we put all of these in the mission equation, and we considered a number of orbits: low lunar orbits, low lunar orbits Keplerian, perturbed Keplerian orbits, restricted three-body orbits in terms of Lagrange point orbits or distant retrograde orbits. And at the end of the day, the winner of the trade-off was orbiting Earth-Moon L2, because on this orbit, we assure 14 days of continuous observation of the lunar far side. As seen from L2, the observation starts when the moon is 50% illuminated. Then you have, as seen from L2, you have the new moon, so 0% illumination, when on ground we have the full moon. And all the way until, again, 50% illumination, which is half of the moon period. Moon period is about 28 days. The science, the cycle of observation lasts 14 days then, which is a pretty good amount of time if you compare it with the few hours that we have on ground on a monthly basis.
Okay. So I'm wondering, as far as the camera being able to see these flashes, if there were any requirements as far as, again, the relative velocity between the spacecraft and the moon, and then if that could affect maybe some false positives.
Yes, because you are almost at rest with respect to the Earth-Moon system, mm-hmm. Relative velocity is extremely low, even there. So there is no requirement associated to that. Also because we are going on, in order to solve for the flash, we are taking pictures of the moon at a high frame rate. Mm-hmm. So we take 15 pictures per second. Yeah. So there is not even time to a portion of the lunar surface to spread to different pixels. Mm-hmm. So that's why there is no requirement associated to that.
Okay. Okay. And I'm wondering also, because I think in the paper that you sent, there was the mention that the CubeSat would get dropped off in low lunar orbit and then do its own transfer to the L2 point. So I'm wondering, kind of the delta V involved in that, some of the trades, and then, first of all, the burn to get out of low lunar orbit, and then how to inject into the halo orbit.
Yeah, so we had two options in the phase A study, which, by the way, was formally concluded today.
Okay.
We had two options, two scenarios. One was the one that you mentioned, so LUMIO to be dropped in low lunar orbit, and the other one was LUMIO to be embarked on the Space Launch System as part of the Artemis 2 mission. The baseline was the low lunar orbit, so we selected orbits that are highly elliptic and highly inclined because these were the one that were most suitable for our purposes. And from that point, in order to go to L2, you have to carry out, to impart an impulse once at the perihelion point. So at the periapsis point of this orbit, you have to implement an impulse in the order of 70-80 meters per second to get to the stable manifold associated to the halo orbit. Once on the stable manifold, then it's extremely cheap to acquire the final orbit. We're talking about 1 or few meters per second cost in terms of delta V. But once there, because the halo orbits orbit an unstable equilibrium point, they are inherently unstable. Mm-hmm. So you have to consider in your delta V budget all of the cost for the station keeping maneuvers. So at the end of the day, this was the procedure that we followed to budget the mission cost and the propellant associated to it.
So I'm wondering what are the mechanisms for doing orbit determination when you're there? Because do you have a line of sight with Earth when you're at L2 or at some points if the L2 orbit is large enough?
Yes, good question. So the other strength of the selected orbit is that there are two points here. One is the following. The orbit is free of eclipse. So okay. We have no eclipses at all in Sun Earth L2 halo orbit. The second point is that the Earth is always visible from the spacecraft, because it's true that you are beyond the moon, but you are not sitting at the equilibrium point. So you are not sitting on the line that connects the Earth and the moon, but rather you are orbiting around it with an out-of-plane motion, which means that if you look at the moon from ground, from the Earth, if you look at the moon, there is a halo all around the moon, and that will be LUMIO, and that's actually the name behind the yellow orbit, which was given by Robert Farquhar at the end of 1960s.
Mm-hmm. So I know this is a pretty complex topic, but I just want to ask you real quick about the manifolds. And you know, there's a lot of background that goes into, you know, the three-body problem and all that. But could you, I guess, give a quick, brief, just explanation, kind of like intuitive understanding of what the stable manifolds are?
Sure. So these objects are associated to equilibrium points, and they are channels. They are channels of free transport in the phase space. When I say phase space, I mean position and velocity space. That you can characterize. So consider you have an inverse pendulum, for instance, okay? Or actually you have a pendulum, but you keep the pendulum on the unstable position, okay? Mathematically speaking, that is an equilibrium point. But if you give an epsilon perturbation to this equilibrium point, the pendulum will escape from its equilibrium position, not return to it anymore. Mm-hmm. So there is an unstable manifold associated to that equilibrium point because the point is unstable. Same thing can be done for the stable equilibrium points. Now, the Lagrange point in the restricted three-body problem, they have both an unstable component and a stable component of the dynamics. But they are called unstable because there is a theorem that says that if you have the unstable component, all the point is unstable, of course. Mm-hmm. Now, associated to these unstable and stable components, there are channels that leave the equilibrium point in forward time, so like the inverse pendulum, and there are other channels that they approach the equilibrium point in forward time, and this is associated to the stable component. The same can be said for the orbits that orbit the equilibrium point. Associated to an orbit, you have channels that will depart far away from the orbit. So associated to the orbit, you can have tubes that depart from the orbit and tubes that will wrap onto the orbit in forward time. So if you are able to extend the second one, the tube that wraps onto the orbit, so the stable manifold, to near the point of departure, and if you are able to place your spacecraft on the stable manifold in terms of position and velocity, okay, that's why you need the delta V, the dynamical system by itself will make it to transport your spacecraft from the injection point all the way to the periodic orbit. It's a complex right. concept, but it's fascinating. I did my master thesis on this, and since then I've been like super fascinated by it. And in fact, after 20 years from master graduation, I'm still talking about it.
Well, can you talk about the end of life considerations for LUMIO CubeSat?
So LUMIO will be disposed in a graveyard orbit. They will not in the long term. So talking about 100-year simulation, will not interfere with neither the Earth nor the Moon orbit. So just simply graveyard orbit. We don't want to crash it on the lunar surface.
Right. Okay. And then for the final question, so I'm just wondering, can you talk a little bit about your decision process back in the day from going from your master's to your PhD at University di Milano, and then also after that, why you decided to teach and why you decided to be a professor?
In my case, well, when I was younger, I was not even thinking of doing the job that I do now. Mm-hmm. I just got extremely involved at the time of the master thesis, because the first year of university studies were like regular, I would say so. But when it came to attend classes on orbital dynamics, that was something that I really liked. I liked orbital dynamics, control classes, numerical analysis, this kind of stuff. So in the end, I got in touch with a professor of mine for a thesis on orbital dynamics, and in particular, I chose this one on the restricted three-body problem dynamics, which was talking about beginning of 2000s. So it was very trendy at that time, I worked on it and I liked it so much that at the end of the master, I asked for if there were PhD positions. So there was a call, and I managed to get the position actually. And I worked on my PhD on a little bit on the intersection between control and dynamics, still applied to orbital dynamics problem. And then I liked it, and then I understood that that was my my path. The path that I wanted to follow was to be a researcher, which I became as an assistant professor, and then I got promoted to associate professor. The dark side of it is that you have to teach, which I don't like pretty much, but it's something that you have to do because the contract is all inclusive. You cannot get rid of it. But at the end of the day, I discovered that I also do like teaching. I do like teaching, especially if I teach what I like, because it's a complex issue, but you're not, sometimes you're not free to teach what you want, but you have to serve the faculty. So you have to teach what they ask you to teach. So it's a complex problem, but if you are lucky that you teach what you like, then it's a win-win situation, because you can be, you know, passionate in what you teach, and you do it without any effort. So at the end of the day, I think I'm happy because I love my job, and if I think that I'm paid to learn and I'm paid to teach what I learn, then I consider myself a extremely lucky person.
All right. Well, awesome. Thank you. Yeah, I think that's pretty much it.
That was 6 o'clock, by the way.
Yeah, right on the dot.
Yeah.
Yeah, well, yeah, that's pretty much all I got. Thank you again for taking the time the past 2 days.
Sure.
I really appreciate it. I learned a lot. And I think a lot of people are going to find this really useful, the stuff that you talked about. So
yeah, let me know when you post this.
Okay.
On what platform do you post your podcasts?
I will do it on YouTube, and then I also post it on kind of the listening apps like Spotify and Google Podcasts. Sure. Yeah, so I can send you all the links.
Sure.
Yeah.
I would be happy to get them because I can circulate them.
Okay, cool. Yeah, that'd be awesome. And yeah, as I said, I think a lot of people are going to find it useful. Even someone already commented because I posted like, oh, I'm going to interview Dr. Francesco, and then someone's like, oh, he was my professor for one of my like intro to mission design classes. Yeah. So I think there might be some Politecnico students.
You posted it where?
Oh, just on YouTube, just like a preview, be like, hey, like I'm doing an interview with him.
Okay.
So yeah,
I'm searching your YouTube channel.
Oh yeah, so basically before I started the podcast, if you just search my name, you'll probably find it. It's I basically just made a bunch of videos on orbital mechanics before.
Oh, I see.
Yeah, and then I decided, oh, I'll start a podcast because it's pretty fun and it'd be fun to talk to a bunch of people just about their job.
Okay, I see you. I see you.
Yeah, so then I posted, well, it's gonna go live tomorrow, the part 1 that we did yesterday. But I think I'm gonna just put it all together and post a full episode probably Saturday.
Great.
Saturday morning for me, Saturday afternoon for you, I think.
Great. Yeah, I see also the comments. Great. Make sure you send me the links. Okay.
Yeah, I definitely will.
Keep in touch. If you pass by Europe, just feel free to get in touch. And
yeah, hopefully when everything opens up again, maybe we'll go to a conference or something in Europe. One of the big conferences. That'd be fun. So yeah, again,
sure. Take care.
Yeah, thank you for everything, and yeah,
thank you to you for contacting, for reaching me out.
Mm-hmm.
Bye.
Bye.